All right, guys, welcome to Notes on Chapter 6, Section 3. We're going to talk about binomial radical expressions. So the goal for today is we're going to be able to add and subtract radical expressions. Big thing here is that we have to make sure that radical expressions work kind of like variable expressions in that we can only subtract or combine like radicals. So for example, right here, the ones they give like radicals with numbers. So like square root of 2 plus 3 square roots of 2 is 4 square roots of 2. Cube root of 7 minus 5 times the cube root of 7 is negative 4 cube root of 7. So these are like radicals with numbers, okay? Here we have like radicals with variables, and it's the same thing, just the variables on the inside. You'll notice x, y, x squared y, x squared y. They got to be the same, okay? We can use the distributive property to add or subtract like variables. So for example, if we had this, we could factor out the a and b, add those, and that gives it for both addition and subtraction. This should look a lot like combining like terms with variable expressions. Combining radical expressions is different from adding them, though, because the values aren't necessarily the same. The sum of any two real numbers is a real number, so we can add square root of 2 and square root of 3 to get the real number. However, we can't combine them into a single radical, and that's proven right here. Okay, square root of 5 equals this, and when we add square root of 2 and add square root of 3, we get this, which is why we can't add them together. All right. So let's take a look. What is the simplified form of each expression? Again, pretty simple stuff here. 3 times 5x, or times root 5x minus 2 times root 5x is just root 5x. Here, the radicands, you'll notice that they're different, so we can't combine them. Here, the indices are different, so we can't combine those. All right. Go ahead and take a second. Try Got It 1A and get some answers. Go ahead and pause the video here and get your answers. Pause it now. Okay, so hopefully you got what I got. 1A, you can't do it because the indices are different. Here we have 7x times the square root of xy, and here we have 2 times the fifth root of 3x squared. All right. Using radical expressions, so here's a word problem example. In the stained glass window design, the side of each small square is 5 inches. Find the perimeter of the window to the nearest tenth of an inch. So you have to remember some quick geometry lesson here, that if the side, if this right here is 5, then this right here is 5 square roots of 2 because it's a square. If you remember that from special right triangles, or you could do Pythagorean theorem and get that. So the length of the window is 3 times 5 square roots of 2, and the width of the window is 2 times 5 square roots of 2. So then we add those after distributing, and we get for perimeter, it's 2 times that, and then 2 times that, and so we end up with 50, and so it's 70.7, so no problem. So find the perimeter of the window if each side, if the side of each small square was 6 inches. So we're going to do this again, but instead of 5, we want you to use 6, which, big hint, that's now 6 times the square root of 2. Go ahead and pause the video here, get that answer, and then do part B also. Part B is just referring to using the Pythagorean theorem, really, that if this is 6, then, and this is 6, then this up here, instead of it being 6 times the square root of 2, if we do the Pythagorean theorem, we get this as square root of 72. That's a 7. This is square root of 72, and each one of these is, and then we could simplify it at the end. Instead, we simplified it up front. Okay, so it's just talking about using that. Let's take a look at what's next. So when we have a sum or difference of radical expressions, we should simplify expressions so that you can find all the like radicals. So this is, our instinct might tell us right away, well, oh, we can't do this one because the radicals aren't the same. They aren't like radicals. But we might be able to simplify each radical and then combine the ones that are the same. So square root of 12 simplifies to 2 square root of 3. Square root of 75 simplifies to 5 square root of 3. And this is a square root of 3. So it turns out, even though these don't look the same at the beginning, we can simplify them. Okay, we can simplify them. So take a look at number 3. We have a cube root now. We have a cube root, and we want to simplify that. So what we need to do, I'm going to tell you, we can add these. You need to find a perfect cube that goes into each one of these. Okay, go ahead and pause the video. Try this problem. When you unpause it, I'll tell you the perfect cubes and give you another shot at it. So go ahead and pause the video here. All right, so the perfect cube that goes into each, this is the cube root of 125 times 2 plus the cube root of 27 times 2 minus the cube root of 8 times 2. Go ahead and pause the video here and see if you can finish the problem. All right, you've unpaused. Hopefully you got, get ready, drum roll, no drums, 6 times the cube root of 2. All right. So anyways, remember FOIL? Remember when we multiplied binomials? We can multiply binomial radical expressions also. Okay, so tons of fun that this is. Say we had this expression times this expression. The same rules of FOIL apply. The difference is at the end, we're going to want to remember that 2 times radical 2 multiplied by 4 radical 2 is going to give me 8 radical 4. This right here gives me 8 radical 4, which is actually 8 times 2, which is how they got 16. Okay? This is just like when we do it with variables. There is literally no difference. All the same rules apply. Go ahead and take a second and see if you can do FOIL on number 4 and get an answer. Go ahead and pause the video here and do that now. All right, you've unpaused. Hopefully you got 46 plus 16 times the square root of 5. If you didn't, make note of it somewhere, and I'll show you step by step how to do that problem in class. We've used this term before, conjugate. We've used this when multiplying things. We're gonna work with these again. Conjugates are expressions where we have a plus and a minus, but everything else is the same. Okay, the only difference is the sign of the second term. When we multiply conjugates with radicals, we end up with no more radicals. It's kind of the nice feature of it. We can use this on problem 6. That's why we have to know how to do this. So we still do FOIL. You square the first. When we do outer and inner, we get terms that add to 0. So really all we have to do is multiply first times first and last times last and get our answer. Go ahead and pause the video. And that's all they did here. 5 times 5 right here for 25. Negative square root of 7 times 5, okay, gives us negative 5 root 7. Here we have 5 times square root of 7, and that gives us positive 5 square root of 7. These two terms in the middle add up to 0. So all we're left with is square the first and square the last. Okay. Go ahead and pause the video here, see if you can get answers to A and B, and we really need to make sure we're getting these because we need them for problem 6. Go ahead and pause the video here. All right, so hopefully you saw that this was 36 minus 12, so that's just 24. And then this is 9 minus 8, so that's just 1. Okay? Sometimes a denominator is a sum or difference involving radicals. If the radical expressions are square roots, we can rationalize the denominator by multiplying the numerator and the denominator by the conjugate. Hence, what I was just talking about, that step of using the conjugate, we are going to need that. So, if we were to try and rationalize this denominator, it has different roots here that can't be simplified. So we're going to multiply top and bottom by the conjugate, which is right here. On the top, we just use the distributive property. On the bottom, we use FOIL like we just did, and we end up with the number 3. We can then simplify this, and we end up with square root of 10 plus 2. Okay? Using the conjugate to get the denominator rationalized. So if we look at A, okay, what we're going to multiply the top and bottom by, and I'm going to show you, make sure everybody understands the conjugate, and then you're going to do it. Square root of 3 plus 5 over square root of 3 plus 5. Okay, that's what you're going to multiply top and bottom by. Over here, we're going to multiply top and bottom by 3 plus the square root of 6, 3 plus the square root of 6. Okay, go ahead and try those, get answers for A and B, and then take a look at C and see if you can get an answer for that too. Go ahead and pause the video here and get those. All right, you're back. A was negative square root of 21 minus the square root of 35. Okay, that's all that we have left. If you didn't get that, make note of it somewhere so we can talk about it. B was 1/3 times 12x plus 4x radical 6. Okay? Part C, suppose you were going to rationalize the denominator of 1 minus square root of 8 over 2 minus square root of 8. Would you simplify square root of 8 before or after rationalizing and explain your answer? My answer is that I would always do it after rationalizing. When the numerator is multiplied by the conjugate of the denominator, it's way more convenient if we haven't simplified yet. So I would say when simplifying, always after. Okay? And that's it, guys. Real short video notes this time. Make sure that you're watching these. Share them with somebody. Get them to watch them just so that we all are starting a conversation from the same place when you get to class. All right? I will see you guys next time. Bye.